As you may have seen previously, in order to form a solution, we first have to break apart the attractive intermolecular forces, here meaning either a normal type of intermolecular force or ionic bonding between solute particles as well as between solvent particles. Both of these involve an increase in enthalpy. However, when the solute and solvent are mixed together, the solute-solvent particles interact with each other, forming a solution. When they interact, there will be intermolecular forces between solute and solvent particles, and this process is exothermic. Depending on whether the solute and solvent particles interactions are stronger or weaker than the solute-solvent interactions, the overall process may be exothermic or endothermic. The process can be endothermic but still be thermodynamically favorable, as the formation of a solution leads to an increase in entropy, as we will examine later. However, suffice it to say that in general, the solute-solvent interactions must be comparable or greater than the solute-solute interactions and solvent-solvent interactions in order for a substance to be soluble. Therefore, what we need to do when we want to evaluate if something is soluble in another substance is to consider the solvent-solute interactions and to compare them with the strength of the solvent-solvent and solute-solute interactions. If the solvent-solute interactions are greater than or comparable to the solvent-solvent and solvent-solute interactions, then the solution will form. However, if the solvent-solute interactions are weaker than the solvent-solvent and solute-solute interactions combined, what's going to happen is that while in a few cases it can occur, in general, unless they are very close to each other, the solution is not likely to form. For example, sodium chloride, when dissolved in cyclohexane, will only have dispersion forces between cyclohexane molecules and the sodium and chloride ions. These dispersion forces are relatively weak and will not counterbalance the loss of ionic bonding in sodium chloride. However, when sodium chloride is dissolved in water, ion dipole forces will be formed between the sodium and chloride ions from the solute and the water molecules. This would largely counteract the loss of ionic bonding in sodium chloride as well as hydrogen bonding between water molecules. In contrast, naphthalene, pictured here, is nonpolar, and therefore we expect to see London dispersion forces only, which is the same forces that would be formed when naphthalene dissolves in cyclohexane. In this case, the solute-solute and solvent-solvent interactions are comparable to the solute-solvent interactions, and therefore naphthalene dissolves readily in cyclohexane. On the other hand, the formation of London forces between naphthalene and water molecules will not counteract the loss of hydrogen bonding within water, and therefore naphthalene is insoluble in water.